I'm asked a lot to talk about, or people ask me what's been new in LLVM, what's been occurring. I'm going to convey as much as I can in a 15-minute talk to a general audience. We'll see how we get on. Obviously, I'm around the rest of the day, so feel free to corner me afterwards. In terms of LLVM, I'll be very brief because I think most people who've come here probably have some understanding of what LLVM is and what it does. It's a suite of compiler toolchain technologies. You're perhaps best known for providing everything that you need for C and C++ development, so the Clang front end, your middle-end optimization passes, back-end code generation, linker, debugger these days. More recently, you'll see adoption for other language front ends, Julia, Swift, and of course Rust, probably the biggest one. And more recently still, development with MLIR, providing a kind of reusable, extensible, intermediate representation. Used a lot in machine learning workloads that can also use more broadly than that. There's a presentation about one use case yesterday that might be interesting to go and have a look at. And of course, it's adopted very widely within the industry, including vendors like ARM, who have retired their old proprietary ARM CC compiler, moved completely over to Clang LLVM-derived toolchains. And I should say, throughout this presentation, I'll be saying a lot about work that's been done within RISC-V LLVM. I've been a long-time contributor there, but I'm just one of many, thankfully. So I'm really talking about work that's been done by a whole range of people across a whole range of companies within the RISC-V and LLVM ecosystem. So LLVM status today. Does it work? Are people using it? Is it actively developed? Yes, yes, and yes. A key milestone that was announced this week was the ratification of RVA 23. That's a good yardstick to use to try and have a look at which instruction set extensions we support. So actually, if you look at all of the mandatory RVA 23 extensions, we have support for them. And although it's wonderful flying out to interesting places and talking about the state of LLVM, you don't need me to tell you what LLVM supports today. You can just go over to this RISC-V usage page. You can have a look, and that gives you a nice table of all of the instruction set extensions which are supported and little footnotes with any provisos about any limitations and that kind of thing. If you have a compiler right in front of you, perhaps provided by a vendor or your operating system, or it was compiled by a colleague, you're not quite sure, you can pass the -print supported extensions flag, and again, it will tell you exactly what the compiler you're using supports. And I guess one aspect I kind of missed off this slide is I mentioned LLVM has a whole bunch of sub-projects. At this stage, LLD, the linker, there's very mature and fairly complete support for RISC-V. I guess missing the recent jump table support from one of the extended compressed instruction set, but otherwise fairly complete. There's a lot of RISC-V support in LLDB. One of the Qualcomm contributors is giving a talk, I think today, a few miles away in the LLVM dev meeting, so I'd go and look up those slides later if you want a full rundown there. And other things like libc++ just compiles and works out of the box. In terms of RISC-V LLVM development, for me, the big success story has been the growth in contributors over time. I started work on this way back sometime in 2016. I'm now one of very many contributors contributing to submitting patches against all aspects of it. Vector has obviously become a huge part of RISC-V LLVM over time. I think it's kind of interesting in that there's a subtly different development model versus most of the other ISAs, I think, in that it feels as though we have more direct collaboration across different organizations, many of those ISAs, and of course, due to the nature of RISC-V specification development, things are developed. You have early versions of the specification released and shared out in the open, so there's much more opportunity to work on them upstream early and potentially have some feedback on the compiler side, but we maybe haven't quite found the best way of closing that loop. In terms of, I guess, key takeaway here would be highlight that in terms of our release process, we have 2 major releases a year. So if you want to know what's going to be in the next LLVM release, the answer is whatever's done when the next release is cut. It's a standard time-based release process. And one thing that I really want to highlight, because I've heard some confusion on this, is that you absolutely can, and in many cases are encouraged to go and submit support for extensions that are not yet ratified, or indeed vendor extensions. So there's considerations that we take into account when doing this, but it's very much not the expectation that you have this kind of fixed process where a specification has a working group, it gets iterated on in RVI, it moves forward, it gets ratified, and then someone goes and writes compiler support and submits it. Or maybe they wrote it and they kind of share it afterwards. Starting earlier, at the point when the specification is getting cleaned, getting towards finalized, can be much more productive. We kind of hide it. We put it behind a flag, a kind of experimental extensions flag, so that there's no guarantee to end users that a extension that's not yet ratified will work tomorrow, just the same as it did yesterday. It may change, it might be removed, there might be ABI changes, but this gives us a really good way of collaborating upstream rather than having these extensions developed in kind of single-use downstream repositories that don't follow the usual code review or development processes. And the same is true of vendor extensions. We don't have a huge amount right now, but there's nothing stopping there's a number of Sci5 ones and some T-head extensions. People are very welcome to submit them. We kind of have a look at what's the potential impact in terms of how invasive it is there a community for it to support it, to use it, and kind of make a consensus-based decision based on that. But in most cases, it's fairly straightforward. A lot of the extensions are relatively simple. It's a small number of CSRs, a small number of extra instructions. In terms of testing, this has been something which I'm very grateful for support from RISE for helping to improve recently. It's an ongoing project. I had a blog post recently, if you go on the RISE website, which talks about kind of where the work is right now. I could talk about it for far too long. I think people are going to stage an intervention against me for having spent far too much time with cross-compiling and CMake configuration in LLVM. But we have quite a nice method now, I think, of doing getting this running on top of a series of builders with different configurations running on QEMU. Not because I'm against hardware-based testing, but for RISC-V, we know we're always going to have to run testing on extensions that are developed, but they're not yet in shipping hardware. And so having that ability to run across a suite of QEMU system emulators is always going to be essential. But of course, as more stuff becomes available, it's great to have the SpaceMIC K1 chip with Vector 1.0 support. We can add more stuff to the build farm. I'll say, and this is also an approach that I know some of the other backends are starting to look at. Some of the ARM people are looking ahead to when AArch32 isn't supported on all of the servers they want to use and thinking of looking at using a similar kind of approach. In terms of performance work, this is an area where I think we can perhaps look to do more and more of sharing our workflows on what we do here. I've had a lot of success personally using QEMU with custom plugins to do tracing. There's been a number of talks about hardware tracing. Fantastic to get data out of real hardware. But if you don't actually need data from real hardware, what's even better is being able to just write some small amount of software code to generate just the information that you want to generate the analysis that you need. That's been super helpful for going and finding things in terms of differences in instruction mixes for different versions of the compiler or for GCC versus Clang. I'm going to talk a little bit about show some performance and code size experimentation I've been done. As with any benchmarking, there's some health warnings. Your mileage may vary. Your workload is not necessarily my workload. I'm looking at a subset of the spec benchmarks and using, the compiler flags can of course have a large impact on this. I'm looking at trying to look at what most people would do, grabbing a compiler tool chain, putting in the correct -M arch and -03. There are other flags that may kind of impact the results that you get, of course. And also there are some further tweaks to these graphs that I would ideally make, but it wasn't possible to make any changes to the slides yesterday morning as they've been they're on the machines, they've been carved into stone slabs or something, and so there's a couple of minor things that I'll note as I go through, but you'll see a finalized version later on if you go on Sched and get the PDF. But obviously, my fault for having a few things I wanted to correct. All my hands up. In terms of where we're at, these are results I got, controlling as much as I can for variation due to I/O, CPU scheduling and the like, so task set onto a single core, dropping all system cache, file system caches ahead of runs, that kind of thing. Looking at so scalar versus vector is basically with or without the V extension enabled across the head as of last week of Clang and GCC. As I say, I'd consider this a sampling of what you might see if you were comparing the two compilers. You could change a lot depending on what benchmark you use, and only a smaller number, not all, actually, a relatively small number of these have are a case where vectorization has a large impact. I guess key takeaways, if you're looking at a story here, would be GCC does pretty well. It beats us in many cases. We've made a lot of progress on vectorization in LLVM, so X264 is a case where vectorization does have a meaningful impact. The vector version of X264 does much better than the scalar version, but still GCC is doing somewhat better than us on the scalar side. I've done, it's maybe not so useful to talk through all of this, but I was looking back at several compiler versions. This is always using the equivalent GCC sysroot of that version, try and control for that variable at least. And also, I'll note this is a case where the error bars for some of these would be a little bit larger than I'd like. So I think on the updated version, you might see a bit more compression of the differences against some of these, as I've been able to run it for a much longer period of time and tweak my test setup a little bit. I think that a nice story there is that LLVM has been, for the most part, getting better over time. We've made progress. These are results for vector code generation normalized against, I guess, the Clang head on scalar. So that's what the 1.0 reference point is. Looking at code size, and just as many health warnings apply to this, it varies massively depending on your workload. mbench is a nice suite of embedded cases. There's an issue here in that I'm missing the GCC OZ result, as this was added a couple of releases ago. You'll see that on the updated slides online. The main takeaway here is, actually, we do fairly well on this, so they're mostly comparable. There are some cases where, I should explain, for OZ versus OS, the difference is that OS is optimizing for size, OZ is optimizing for size, but paying less or little, maybe no attention to the impact on performance. So you're able to do much more aggressive optimizations that might hurt your runtime performance. An example of that we do on LLVM is machine outlining. So identifying sequences of code that are repeated across your input and then pulling them out. I should say this is without LTO because some of the mbench benchmarks have the issue of effectively compiling away to nothing with LTO, but that's another variable that can impact this. I guess the main one to highlight for fairness is that an outlier here, the Nettle SHA-256, that we're doing a fair bit better than GCC on it. Actually, GCC catches up quite a lot with OZ. It's roughly comparable. In terms of things to highlight from recent improvements, and I guess there's a broad definition of recent here, there's been work going on over the last couple of years. I'll highlight a few things that are of interest to me. The growth of scheduling models, particularly as we have more and more real hardware available. That's both exciting. There's also a really fun little technical project here around the project called LLVM Exegesis. Min at Sci5 is talking about that either today or tomorrow at the LLVM dev meeting, which helps you extract things about the microarchitecture automatically without having to go and necessarily write all these details yourself. There's another bit that I'd highlight that I think I haven't mentioned here, which is a nice example of different people trying to use a tool chain in different ways, finding something they need to do for their use case, and then contributing it back up. And that's recent work to extend the .instruction assembler directive. I've given a whole bunch of talks about, or tutorials on extending LLVM to add support for new instruction set extensions. I always like to highlight, if you can get away with it, the easiest thing is, of course, not extending LLVM at all. The .instruction directive makes it quite easy to assemble your own instruction, but there are issues around it didn't support experimenting with 48-bit or 64-bit encodings, gaps in terms of the specifiers, which registers to use. I think there's further work coming down the line to support relocations there, which is super nice because it gives a nice way of achieving more of that fast iteration on proposed instruction set extensions that we maybe haven't quite succeeded in doing in the best way possible in the RISC-V community so far. In terms of how to get involved, you can look up a tutorial or slides are online of a talk I gave at the RISC-V Summit Europe earlier this year. One of my colleagues, Luke, did given a really good write-up of how RISC-V vector code gen works, which, particularly if you're looking to work in that area, is very helpful to get involved. Come by the bi-weekly coordination calls that I arrange, or otherwise drop by. I guess a final thing to get on my soapbox about is, if you're working with a downstream tool chain, that's great. I've got nothing against downstream tool chains. What I'd suggest, though, is that you ask your vendor, the person providing that tool chain, what's the difference between upstream? Are you looking to reduce the patch set? It often makes a lot of sense to have things downstream for a while. It can take a while for things to bake, but I hope that we can continue to move more and more of this stuff upstream, which helps ensure that you're using newer stuff that's available. A couple of things I'd highlight for future work. There's a lot going on there. Function multiversioning is a major one. It's a kind of thing that you'd think surely we have by now. It's taken a while to agree things like the interfaces. As you know, a big challenge with RISC-V is that we have lots of variants of different instruction set extensions that are supported. You need an easy way of having a function compile it across different ISA variants and then select which one the hardware actually supports. That's going to be a key thing, I think, on the next LLVM version, particularly as more and more hardware that moves beyond the RV64GC baseline becomes available. I think I'm very short on time, and I know we're a bit behind schedule anyway due to the alarm, so we may or may not have time for questions, but feel free to come and talk to me over lunch or drop me an email. I'll be happy to answer anything. Thank you very much.